Welcome, friends. So we are here to discuss about the overview of power system. That is the beginning of the course. So let us start with the discussion. What is power system? As I already told you, power system has three sections mainly: generation, transmission, and distribution. Generation deals with the generation of power. Transmission deals with the transmission of power over a long distance, and distribution is distribution of power amongst different types of consumers. So power system generally comprises of three components. One is generation, thereafter transmission, thereafter distribution. So there are different power stations like thermal, nuclear, then hydroelectric, wind farm, solar. Then it is transmitted over a long distance, and at the last stage power is being distributed among various consumers, like we have industrial consumers, like we have steel plants, Indian Railways. We have commercial consumers like different shopping malls, stadiums, restaurants, etc. And finally, we have domestic consumers like we are the household customers. Now, to discuss the entire course module, the module 1 comprises of overview of power system. Thereafter, we shall shortly discuss about the transmission line. It has two aspects. Number one is transmission line constant, that is about the inductance of the transmission line and the capacitance of the transmission line. Subsequent to this, we have performance of the transmission line, that is the categorization of the transmission line and its performance. Then we have corona. It has nothing to do with the coronavirus. Then we have sag tension, and of course a very important topic, it's insulator. At the last stage of this course, we need a short introduction of compensation, why it is needed. Then we have another mode of transmission and distribution of power, that is underground cable. And finally we have distribution system. So this is overall the structure of this power system 1. Now this is the overall structure of the power system. Now the data mentioned in the diagram is the rough data. It may vary. Now at the first stage, it is the generation of power. As you can see, it is generated at 11 kV, right? It is generated at 11 kV. Thereafter, that power is being injected to the transmission line. So immediate task is done is that power or voltage level at the generator side is being stepped up to 400 kV. Then starting with the transmission of power, it has got two sections. One is primary transmission. After carrying power to certain distance, that voltage level is reduced to 66 kV. And relatively at the lower voltage, we have secondary transmission conducted. Now, this is the end of the transmission stage, where this transmission voltage is again further stepped down to 6.6 kV. Now at this 6.6 kV or maybe at 11 kV, the power supply is given to the industrial consumers like different plants, Indian Railways, etc. Now here it is from this bus, the distribution is started. The primary distribution is being conducted at preferably at 6.6 kV or maybe at 11 kV. The conductor through which the distribution is conducted is called feeder. Now that feeder is carrying power to our locality. Each transformer is rated 6.6 kV at the primary, and at secondary it is 415 volt. Now these transformers are located in your locality. So this transformer, the output, that's the secondary of the transformer, you are getting the supply. So we have domestic consumers, we are getting single phase AC supply. Also, from the secondary side of the transformer, commercial consumers like shopping malls, restaurants, stadiums, they are getting three-phase power supply. Now, this is the overall structure of the power system. It starts with generation of power. Typical generated voltage is 11 kV. Of course, it may vary, but mostly it is used 11 kV. Then it is stepped up to the 400 kV. Then transmission has been conducted. It has got two stages. One is primary transmission, then we have a secondary transmission. Once the transmission stage is done, distribution is started, and at the very beginning of the distribution, industrial consumers are given power. Primary distribution is typically conducted either at 11 kV or 6.6 kV or something related similar to that voltage. That feeder brings power to our locality, to the transformer. It is situated in our locality. This transformer is called distribution transformer. Okay, this transformer is called distribution transformer. From the secondary side of the transformer, domestic consumers are getting single phase AC supply and commercial consumers are getting three phase AC supply. Now this power system, this structure is called classical power system. Why it is classical, I will tell you in a moment. This model or this structure has been adopted from the very beginning of the electrical industry: generation, transmission, distribution. That is why this scheme is called classical power system. Of course, this is my nomenclature. You do not hear this on any books or anywhere else. This is my nomenclature. So as I told you, the typical generation voltage is 6.6 kV, 11 kV, or maybe 15.6 kV, 22 kV, and maximum up to 25 kV. Again, this power is injected at the transmission lines, and while doing that, voltage is being stepped up. Typical transmission level voltage is either 220 kV or 400 kV or 765 kV. So highest transmission voltage available in India is 765 kV. Now transmission has got two parts. One is primary, another one is got secondary. Primary transmission is being conducted at relatively higher voltage. Secondary transmission is being carried relatively lower voltage like 66 kV. Now it is must to use the high voltage transmission. While generation voltage is only 11 kV or 15.6 kV, that voltage must be stepped up to 400 kV or 765 kV. This is must. At the end of the secondary transmission stage, industrial consumers are given power. This is already mentioned. Then coming to the distribution of power, primary distribution is conducted preferably at 11 kV or 6.6 kV by feeder. That is the conductor which brings power to us. That is called feeder. Now secondary distribution is started from the secondary of the distribution transformer and is done at 400 volt by distributor. Okay, this is another type of conductor used in distribution system. Commercial consumers like shopping malls, stadiums, restaurants are given three-phase supply, already mentioned, and domestic consumers are given single-phase supply. Now, when we are talking about the classical power system, now over the year, power system has evolved a lot. Generation side, transmission side is okay, but with the advent of distribution generation like solar, wind, there is a tendency that power is being injected to the grid with the help of this power, solar or maybe wind, at the distribution levels. So this is the evolution is taking place or is being taking place nowadays. So we can generate power, we can inject that amount of power to the grid at the distribution level. So this is a very encouraging thing for us, okay, to inject power at the distribution level. So if we do that, what is the advantage of that scheme? First of all, the first advantage is with the high penetration of DG like by solar, wind, etc., power can be generated at the distribution level. So we somehow may overlook these transmission sections, or in other words, we can say we somewhat lower our dependency on this transmission system. Okay. One of the prime concern of today's world is the carbon footprint will reduce drastically because they are green energy. As I already told you, third point, this will reduce the dependency of the conventional power generation. As you can see, if this solar or wind, that is the distributed generation, can contribute 10%, 20% of the total generation, then we can reduce the conventional power generation by that amount. Okay, so that is plain and simple. So we somehow we are putting our leg forward to the independency towards the generation of conventional power. Also, this will reduce the loading of the transmission line. What is the meaning? Like I say, suppose demand is, for a particular instance, suppose demand is 1 per unit. Okay. Suppose demand is 1 per unit. When there was no DG 15-20 years back, then this power, this demand has to be entirely catered by this conventional energy or conventional source like coal, nuclear, etc. However, if out of this 1 per unit demand, let us say this distribution generation can meet 25%. So it is injecting 0.25 per unit power to the grid. So now what is actually what we can have advantage that the conventional source has to feed only 0.75 per unit of power. Only 0.75 per unit of power, because rest 25% of power is being injected by the solar or wind. So initially the total loading of the transmission line was 1. But with the advent of these technologies, now it is drastically reduced by 25%. So this is the way the loading of the transmission line can be reduced. Okay, this is another extremely good advantage we can have from this distributed generation. Now, often you will come across this question, why high voltage is needed while transmission of power? This is very important question often you will face in your academic career. Means suppose you see the generation is being done at 11 kV. At the end of this power system structure, we have only 415 volt. So why not using only one step down voltage to make this 11 kV to 415 volt? So why needs stepping up that voltage? So why require this much of steps? The reason being, you know a very well-known relation, P is equal to VI cos phi. P is equal to VI cos phi. Okay. So from there you can get I is equal to P by V cos phi. This well-known expression you should know. Now you can see that suppose we will transmit constant amount of power. So our P, let us say, constant, and we will have our power factor is constant. So if our P constant and power factor is constant, then you can see that current is inversely proportional to the voltage. Current is inversely proportional to the voltage. So that is the thing, it is written, current will reduce drastically with the increase in high transmission voltage. So if voltage goes high, current becomes lower. Voltage goes high, current becomes lower. Now what will be the consequence if current becomes lower? So if the current becomes lower, conducting material will be reduced. That is, the diameter of the conductor will reduce, so that will incur lesser amount of cost. Now if the current will be reduced, then that I square R loss, that is the copper loss, that will also be reduced. So that is, power loss will reduce. So if the power loss will reduce, efficiency will improve. Lastly, if the current will reduce, then I into R, that is the voltage drop, also reduce. Voltage drop will also reduce. So what will be the effect of voltage reduction in voltage drop? Voltage regulation will improve. That means the consumer will get better voltage profile. So these are the reasons. In terms of current, of course, if we can able to enhance voltage at the transmission line, our current will reduce. So if current will reduce, the conducting material will get reduced. We will require lesser amount of conductor material. If the current is reduced, then our I square R loss will be reduced. As a result, our overall power efficiency will improve. Lastly, if the current will reduce, IR drop, that is the voltage drop, will reduce. As a consequence of that, voltage regulation will improve. Okay, so what is the meaning of that? The consumers will get the better voltage profile. Now, why high voltage is needed? That can be explained in another way. Suppose, let us say this is a power system. We have a generator and we have a load, and in between we have a transmission line. The generator side voltage is E delta, load side voltage is V0. These angles are associated with the bus. As they are the phasors, so it must be accompanied by it must have a magnitude as well as the angle. So power injected by that generator, if it is a P, then P can be represented as EV by X sine delta. This is the expression. Power injected by the generator and which is being transmitted by this transmission line and to be fed to the load. That P is EV by X sin delta. Now from the expression you can clearly see that P is directly proportional to the product of the voltages associated with the two buses. What is E? E is the voltage at the generator side. What is V? It is the voltage at the load side. So it is the product of both. So if the transmission voltage is 11 kV, you can imagine or you can understand what will be the amount of power transmitted. And if the transmission, on the contrary, if you think that if the transmission voltage from 11 kV it is made 400 kV, so what will be the amount of power transfer? So it is huge. So to transfer or to transmit bulk amount of power, high voltage transmission is quite necessary. So these are the two reasons we can adopt a high voltage transmission. Okay. Now another important thing that it is the term compensation. What is compensation? Suppose we have a distribution system. This is the consumer one. Okay, this is consumer one is tapping current I1. This is the current I1. It is tapping. Consumer 2 current tapping is I2. Likewise, we have n number of consumer. In nth consumer is tapping current IN depending on their load pattern. Let us say consumer 1 is using fan, light, AC, refrigerator. Consumer 2 may be using some different loads. In this way, different consumers are using different loads. So accordingly, this generator will feed different amount of current. Summation of all these loads. And for the sake of convenience, you just imagine this generator 2, that this generator is not there. This is something, some other networks are there. Now the more this, the more current drawn by this generator, you see this is feeder. Okay, this is actually feeder. Now feeder has a definite resistance. Okay, feeder has definite resistance, right? So the more current it will draw, the more will be the drop along of the length of the feeder. So suppose the generator has got 100 volt. I am giving you a rough idea. Suppose consumer 1 is getting a voltage of 99.9 volt. Okay. But when it comes to consumer 2, it may get a voltage of 99.7 volt or 85 volt. Okay, or 99.8 volt. So the more you go away from the source, more will be the voltage drop. So the consumer sitting at the far end will get the lower voltage. Understood? Because this much section has a definite resistance, so some drop will accompany. Again, this much section has some resistance, so this will also have some voltage drop. So in this way, more we go away from the source, the more will be the voltage drop. In this way, the consumer sitting at the far end will enjoy the low voltage profile. That is the problem, because tariff set by the generating company is same for everyone. Suppose consumer 1 is paying ₹5 per unit of the power. So nth consumer is paying the same. Nth consumer is paying the same. So why should nth consumer be penalized? So that is the thing, that from here it comes the necessity of the compensation. what it does is actually at the load side or at the far end, here maybe a compensating unit is installed. What it does, it injects leading var into the system. It injects leading var into the system so that it can compensate lagging var. It can compensate lagging var so that this voltage level will again come closer to this 100 volt. So this is the principle of compensation. This is how the compensation works. So up to this, I am concluding here. I am stopping here. From the next class, the next topics will be discussed. Thank you.